So here we go. So I guess the first question is, do we have to do this? And I guess the answer is yeah, because chemistry has a lot to do with being a paramedic. You cannot understand how the body works, its physiology, without knowing about its chemistry. You can't figure out how drugs are going to act on the body, our pharmacology, without it. The language of chemistry is part of the language of medicine, and it's going to help you understand why patients look the way they look. And those are just important elements. If we were all in the same place at the same time, and you have been, if you looked around, you're going to see a whole bunch of people that are incredibly different sizes and shapes and colors and hair color and absence of any hair of any color. And as individual as we all are, thankfully for chemistry, we are all remarkably the same. Our organ systems and the functions that they provide are pretty much the same. At least they are when we come off the assembly line, before things happen that change them or before we do something to change them. So we're going to talk about the basic ingredients that make our physiological systems do what they're supposed to do, how they're designed to do it. And in doing that, we're going to pour a foundation for understanding what can go wrong that's going to lead somebody to dial 911 and put you right in charge of recognizing what happened to them, what aberrations took place in their chemical physiology that made them call, that made them have the symptoms they do. So you can select the right intervention to restore them to their optimal state. So we're going to start at the basics and we'll build out to some things that are pretty complex. But I think if you have ownership of this, a lot will make sense to you as you go through all of the rest of the curriculum in terms of how the body is supposed to work and why people look the way they look when it doesn't work right. So we're going to start very basic. And basically, we're going to start here. Everything is made of matter. Anything that has weight, takes up space, that's matter. And it comes in three main forms: solid, liquid, and gas. And all the matter is made up of chemicals: water, metals, gasoline, extinguishing foam, and us. And chemicals can cause medical emergencies. A diabetic takes too much of his chemical insulin and becomes unconscious due to too little of his chemical glucose. Acetylcholine is a critical chemical messenger for our nerves and muscles. It's manufactured in our nerve endings, and then once it's released, it splashes across onto the targeted muscle receptor site and stimulates that muscle to contract. And once its job is done, there's another chemical called acetylcholinesterase, which basically breaks it down and resets the whole neuromuscular junction interface. There's another kind of a chemical called an organophosphate. You probably know of it or have heard about this chemical before. It's used in agriculture. It blocks our naturally occurring acetylcholinesterase, which leaves the acetylcholine to be unbroken down. It hangs around longer, which means that the muscle contraction lasts longer. If you were a tiny little insect that goes about eating romaine lettuce in the fields, an organophosphate treatment is too much for the little nervous systems of those insects, and they just fire off whatever muscles they have, and that's the end of them. They can't tolerate the overload. I show you this slide because there's a chemical agent called sarin. It is an organophosphate. And in March of 1995, a terrorist group released sarin gas into a subway in Tokyo. And it left the muscles of the people who were exposed to this gas discharged because the acetylcholine couldn't be broken down. So their muscles went into this permanent state of contraction, which means their diaphragm, their respiratory muscles, and 12 people were killed and 5,000 were injured by this. We treat these kinds of poisonings with other chemicals. One is called atropine and one is called pralidoxime or 2-PAM. So the atropine competes with acetylcholine for binding to the muscles. So it helps to restore muscle contraction capability. And the 2-PAM pulls the serin off the acetylcholinesterase molecule, allowing it to work normally and break down excess acetylcholine and restore the balance that we need between firing off and contracting and then relaxing again. So this is something that is in the caches for disaster preparedness. And that's the chemistry that matters. Another one is we may have a patient with kidney failure who may go into a cardiac arrest because of too much of a chemical called potassium. The heart needs a balance of potassium in order to be able to contract properly. And if we get too much potassium, the heart will stop. So when we learn about how chemistry works in living organism, we're talking about biochemistry. And biochemistry is the study of the interaction between atoms and molecules. It's the simplest organization of the body at the chemical level. Biochemistry is the study of the chemical aspects of life. Bio is life, and chemistry is chemistry. So, given that as an opening hit, let's break it all down. All matter is made up of chemicals, and chemicals are made up of atoms. And atoms are made up of 3 parts. There are protons, which are positively charged. There are neutrons, which have mass, but they don't have any charge. And then there's electrons, which sort of fly around the nucleus and have a negative charge. All of the elements naturally have atoms, and atoms naturally occur in any of 92 different types of elements, okay? So there are 92 of these that are found in nature. There are another 26 that have been synthesized by man to give us a total of 118. Element 118 is organesson, and it is named after a Russian nuclear physicist, Yuri Organessian. It's the number of protons, the positive charged particles inside the core, inside the nucleus, that determines which element it is. So the number of protons is called the atomic number. So sodium, for example, has 11 protons. So anything with 11 protons has to be sodium. Anything with 26, it's got to be iron. If it has 53, it is iodine. That is its brand. That's its stamp. That tells you what you're dealing with. So every element also has a symbol. Hydrogen has 1 proton, so its atomic number is 1, and its symbol is H. Helium has 2 protons, symbol is He. Lithium has 3, Li. Carbon 6. Oxygen has 8. So anything with 8 protons has got to be oxygen. That's its atomic number. That's its signature, and so on. So you can sort of get a handle on these, on the abbreviations for what these are. Uranium has 92 protons, so its atomic number is 92. That nucleus is pretty crowded. There's 92 protons in there jammed in, okay? What's interesting is that 96% of every one of us is made up of only 4 elements: hydrogen, oxygen, carbon, and nitrogen. 96% of each of your body weight is made up of hydrogen, oxygen, carbon, and nitrogen. And if you sprinkle in a little bit of phosphorus and sulfur, you will find this in all living things. the atoms are the smallest unit of an element, okay? And the atoms of the same element have to have the same number of protons, right? They could have different number of neutrons. Look, for example, here. Here's mercury, okay? An atom of mercury has 80 protons by definition. It also has 121 neutrons packed in its nucleus. They have mass, they don't have charge, okay? So the number of protons, which has mass and charge, and neutrons, which has mass and no charge, if you combine those, you get the atomic weight. That's the weight of an atom of mercury. So the weight of an atom of mercury is 201. Potassium has 19 protons, 20 neutrons. Add those together, you get 39. That's the atomic weight of potassium, and so on. Now, take a look at this. Hydrogen, we said its atomic number is 1, right? So it has 1 proton. Here it is. Here's a hydrogen atom. 1 proton, it has 1 electron. What happened over here? Somebody pushed a neutron into the nucleus of hydrogen. It still has 1 proton. Its atomic number is 1. But now its atomic weight is increased because we've got more mass in there. It's still hydrogen. It's a heavier form of hydrogen. Some people call it heavy hydrogen. Because it has 2 particles in the nucleus, it's called deuterium. And tritium has 2 neutrons in there. Tri is 3. So its atomic mass is, 3. But it's all still 1 proton. They're all different forms of hydrogen. And those are called isotopes. They have the same atomic number, 1, but they have different weights because there are different amounts of neutrons in there. So those are hydrogen isotopes. The other thing to keep in mind, and this plays a big role, is that atomic particles are charged, right? The protons have a positive charge. The electrons that are orbiting have a negative charge. Neutrons don't have any charge, so they're sort of non-contributors to the charge, to the overall charge. If the number of protons equals the number of electrons, then they balance out, positive and negative, sort of cancel each other out. And the atom itself, the lithium atom, has no net charge at all. It's neutral. Okay? The atomic number is 3. The atomic weight, the atomic number is 3 protons. The atomic weight incorporates the other neutrons in there. But the number is 3 protons, 3 electrons. So we have a neutral lithium atom. It is not charged. Okay? If we charged it, we call it an ion. Look at this. Here's the lithium, 3 protons, 3 electrons. If it loses an electron, then it has a net positive charge of +1. 3 positives, 2 negatives. Okay. It's still lithium, but now it has a net positive charge. It's a lithium ion. And the reason we need to understand this stuff is because it matters when we start to consider the chemistry of how our body actually does what it does. For example, how our nerves send impulses and our heart contracts and pumps. If an electron is gained, then you'll have a net negative charge. Here's chlorine. Okay, it has 17 protons and 17 electrons. If it picks up another electron from someplace, now it has a net negative charge. Okay, so now it's got a -1 charge. And some atoms can gain or lose 2 or more electrons. This is beryllium. It had 4 protons. When it was neutral, it had 4 electrons. It lost 2 of them. So beryllium has a beryllium ion has a net charge of 2+. And calcium and magnesium also can do that. They can lose 2. Okay. Electrons orbit around the nucleus in different shells. They're called shells or energy levels. The first shell can accommodate 2 electrons. So hydrogen has got room for another one, but right now it's neutral. Here's its first shell, one electron. Helium's first shell is full. It's got 2 electrons in there. That's all it can accommodate. What happens if we wind up with more electrons, like lithium that has 3? Well, the first shell is filled up with 2, and then the third one winds up in the next level of shell. So the first shell can accommodate 2. The next one can hold a total of 8. Okay. Here's neon. It has 2 in its inner shell, and it has 2, 4, 6, 8 in the next one. So it's full. The first shell is full with 2. The next one is full with 8. The third shell can hold up to 18. And the fourth one could hold 32, and then 50, and then up to 72. So these can be massive amounts of electrons, all orbiting around a given nucleus. So you could guess that the amount of energy that the electrons going in these outer shells, they're very energetic electrons. An atom is happy when its electron shells are full. So if the outermost shell isn't full, then the atom is not full. It's not satiated. Okay, it's got room to pick up another one. Okay, so an unhappy atom is going to do whatever it needs to do in order to become happy. Okay, here's lithium again. It's sort of our model. It's got a full inner shell with 2 electrons, and it's got 1 electron in its outer shell, which can accommodate 8. So what would make it happiest? To go scrounging around looking for 7 more to fill up this outer shell, or take a lesser resistance path and say, you know what? You're leaving. I will ionize. I will get rid of that 1 solo electron in a shell that can have 8, and I'll be a very active ion, and be a negatively charged, a positively charged ion. I'll have 3 protons, but only 2 electrons. Sodium will do the same thing. Sodium has 11 protons in its balanced state, okay? So there's 11 protons in here. It's got 2 electrons in its inner shell. It's got 2, 4, 6, 8, so it's got a full 8 in its next shell. That's 8 and 2 is 10. And then in the next energy level, which could accommodate 18, it's only got 1. This is a really active electron, and sodium wants to reduce its solitary electron that's occupying a higher energy shell, and it's going to want to ionize and get rid of it. So metallic sodium is a very active metal. It's a lot easier to get rid of that 1 electron than to go shopping around for 17 more to get 18 in that third shell. Sodium metal is so reactive that it reacts with water to form sodium hydroxide and release hydrogen gas. Okay, you may have experienced a demonstration like this in high school chemistry, where metallic sodium is kept wrapped and not exposed to air, and then when it's open and exposed to the air, the sodium is so active in getting rid of that 1 last ion that it actually breaks down the moisture in the air, releases hydrogen from the H2O moisture in the air, and ignites it. So it'll basically precipitate a fire. Okay. So here's fluorine. Okay, fluorine has a full inner shell of 2, and it's got 2, 4, 6, 7 out of 8 in its next shell. So how this one get happier, is to very actively seek 1 more electron from someplace to fill its capacity to 8. And fluorine does that a lot, and it becomes a fluoride ion, a -1 net charge. We use symbols to describe ions. Sodium is Na. A sodium ion has 1 plus charge, so it's Na plus. Potassium ionizes with 1 positive charge. Its symbol is K plus 1. Hydrogen +1. Calcium can lose 2 electrons and it'll become +2, and magnesium can do the same. Chlorine will pick up an electron and become a chloride ion, -1. Fluorine does the same. Positive ions are called cations, and negative ions are called anions. Okay. All right, big deal. We've got elements and atoms and ions. So what? It's what they do that has anything to do with us, with our human functioning. And what they do is they make things. So atoms can connect to each other to form more complex structures called molecules. Okay. These are two different molecules that are stuck together. Chemical formulas either list how many of each atom there are. This is 3 carbons and 8 hydrogens, C3, and then 8 hydrogens. This is C6, 1, 2, 3, 4, 5, 6 carbons, 12 hydrogens, and 6 oxygens. So it lists the atoms and it tells you how many of each are in a molecule, but they have no idea telling you how they're connected, what's holding them together. Anybody know what this first one is? You can just unmute and tell me if you do. This is propane. Okay. This is your barbecue. Anybody know what this one is? C6H12O6?
Glucose.
You bet. It's probably the most important thing you're going to see going forward. This one is key. But a more realistic picture of molecules is that they're 3-dimensional. If this is H2O, there's sort of a 3-dimensional configuration to the atoms and how they align themselves between the hydrogen and the oxygen of water. So they're a little more like scoops of ice cream. Some of these can get pretty complex, as you could see, these molecules. And some molecules could be made up of just one kind of an atom, like O2, 2 oxygens stuck together, Cl2, 2 chlorines, H2, 2 hydrogens. When you have a molecule that has more than one kind of an atom in it, like H2O or propane or glucose and stuff, more than one element, those are called compounds. So we've heard of propane and glucose, and how about H2O, water, NaCl, salt? Okay, these are common things. So it's things we're familiar with, but we may not have thought about it in this way. So to understand how these atoms actually combine with each other, we need to understand a little bit about bonds. How do they bond? So here's some types of bonds. There's that bond. There's those kind of bonds. And then, of course, there's that bond. But we're talking in chemistry about ionic bonds, covalent bonds, and hydrogen bonds. Ionic bonds are based on one basic principle, which is that opposites attract. Okay. So ions with opposite charges will attract each other. If I have a positively charged ion near a negatively charged ion, like opposite poles of a magnet, they will try to stick together. Sodium and chloride form an ionic bond. So here's the sodium ion, okay? Here's sodium. It's got its inner shell, it's got 2, 4, 6, 8, and then it's got this 1 hanging around over here. It's going to get rid of this if it can, okay, and become a positively charged ion. Chlorine is very hungry for 1 electron in its outer shell, and when it picks it up, it'll become a negatively charged ion. So the positively charged sodium and the negatively charged chloride will stick together. They'll bond together. And it doesn't just bond together like it does in this picture. When sodium and chloride bond together to form salt, to form sodium chloride, they align themselves in a specific way that actually forms a crystalline structure, which looks like chunks of salt that you see. table salt, rock salt, things like that. And so the chlorides here depicted in purple align themselves so that they're stuck to a sodium, which is depicted in green. So they're all neatly organized, staggering together like a puzzle. So ions can either donate or receive an electron, which gives them either a positive or a negative charge. If they give one up or they get one, they have an unequal number of electrons compared to the number of positively charged protons in their core. And that creates the charge of the ion. Oppositely charged particles attract each other. And ionic bonds are what holds those molecules together. Okay. So an atom with a net electrical charge, positive or negative, we call that an ion. Cations have a net positive charge. Anions have a net negative charge. Ionic bonds are sort of so-so in the solid state, but they're weakened in water. The molecules will ionize again, and they'll come apart. They'll dissociate into their free sodium and free chloride ion. Okay. Go ahead and just unmute and talk to me if there's a question. Okay. So ionic bonds are fairly weak. They can be broken down by adding water. You can dissolve salt in water and make salt water. In ordinary life, we call that process dissolving. The sodium chloride is soluble. It will dissolve in water. And that's really it for the ionic bonds. So the ions are either positive or negative, and if they are in close proximity, they will form a union, which can be broken down in the presence of water. It can be dissolved. Let's talk about covalent bonds. They are way stronger, okay? They're much stronger because the atoms involved are actually sharing the electrons with each other. So rather than losing an electron and becoming positive and picking up an electron and becoming negative, and then we can sort of, we can stick to each other, these are sharing their electrons across each other. So let's look at this one. Are these atoms happy? Well, no, because here's oxygen. It's got 2 here, and in its outer shell, which can accommodate 8, it's got 2, 4, 5, 6. It would love to find another couple of electrons to sort of fill this out. Hydrogen, on the other hand, only has 1 electron. It's got room for another one in its inner shell of 2. Okay, so I have this hydrogen has an electron. It would love to sort of borrow that one and maybe share it. This one has 1 electron. Wouldn't it be nice if I could sort of share these together? So, in the words of Bobby McFerrin, don't worry, be happy. So we follow the traditional US economic model of borrowing will make me happy. And what happens is these electrons are mine, but I'll share it with you. Okay, and this one is mine, I'll share it with you. And so it's sort of an extended loan obligation where the hydrogen ions each lend their 1 electron to the oxygen. So 2 of these are each lending an electron. That's 1 for you, 1 for you. And now the oxygen's second orbital shell is seeing 8 most of the time. Covalent bonds are formed by atoms that share electrons. A single covalent bond shares 1 pair of electrons. Okay, and we indicate that by a single line when we write the chemical formula. I'll show you in a sec. Double covalent bonds share 2 pairs of electrons, and that's indicated by a double line. These are harder bonds to break. They're much stronger than ionic bonds. So if I have a hydrogen sharing with another hydrogen to make a molecule, an H2 molecule, they are sharing 1 pair of electrons. Oxygen is sharing 2 pairs of electrons, 2 from each. So it's indicated by the double line. Carbon dioxide is sharing 2 pair of electrons here and 2 pair of electrons here. It's got 2 double bonds, CO2. And nitric oxide will share 2 pairs of electrons as well. So that's a double bond. Okay. Any question on that at all? You can take a kind of a breather here and think about this. Okay, so just to keep in mind, the shared electrons are orbiting around both atoms. So they're forcing these things together by the electrons orbiting around both, rather than an ionic bond, which just sort of sticks together because there are charge differences. Our third kind of a bond is called a hydrogen bond, okay? These occur between water molecules. Now, bear with me for a sec when we talk about astronomy, okay? Chemistry wasn't enough. Let's look at this for a second. Think of Jupiter. It's a massive planet. And it's a massive planet, so it has a massive gravitational force. Earth, by comparison, is pretty small. Jupiter's gravitational force is almost 2.5 times greater than ours. That means that if you weighed 170 pounds here, you would weigh about 410 pounds on Jupiter, because its gravitational force is so, its pull is so great on our body mass. Now let's go back to this water molecule again. In this example, the hydrogen and the oxygen are bound together by covalent sharing, right? They're sharing electrons. But oxygen is so much more massive than hydrogen that it pulls the electron cloud more toward its side than on the hydrogen side. It tips the electron that's orbiting both of them more toward the bigger atom. What that means is that the electron orbiting here spends a little more time on the oxygen side of the molecule than it does on the hydrogen side. That means that the oxygen side is a little bit more negative because the negative electrons are spending more time over on this end of the molecule. It also means that because it's spending more time over here, it's spending less time over here, which means that the hydrogen's one proton is exposed more because its neutralizing electron is hanging around on the oxygen side a little bit more. So the oxygen end of a water molecule tends to read a little bit more negative, and the hydrogen sides tend to read a little bit more positive, and that's indicated by these little pluses here compared to the 2 electrons hanging around over here. So it's a little slightly negative on this side. What that means is that water molecules are going to stick together because of hydrogen bonds. So if we look at all these water molecules, and we know that the oxygen end of the molecule tends to be a little bit more negative because the electrons hang around there a little bit longer, and the hydrogen sides tend to be a little bit more positive because those electrons are over here, and their positively charged protons are unopposed, that the water molecules will orient themselves so that the negative side of the molecule, the oxygen side, is going to turn itself so that it faces the more positive side of an adjacent water molecule. So the oxygens point toward the hydrogens of a next door molecule. Same here. This hydrogen is pointing toward the negative side of this oxygen. This negative side of the oxygen is pointing more toward the positive side of this one. And this is what makes water water. The relatively positive hydrogen ends of one water molecule are attracted to the relatively negative oxygen of another neighboring water molecule. They're still shared, but they're shared unequally. Okay? So that's what gives water its cohesion. So it makes it stick together. Hydrogen bonds are weak forces between a slightly positive hydrogen atom and a slightly negative oxygen atom. Okay. Sometimes nitrogen will do this too, and possibly even another hydrogen, but by far the most common is between H2O. These weak bonds are really easy to break. They're broken by changes in temperature, by changes in acidity, the changes in the environment that the molecule is living in. But this is what makes water cohesive. It's what makes water stay as the liquid that we all know. So with shared electrons like this, if the electrons are attracted more to one atom, in this case, more to the oxygen side than the other, the hydrogen side, then the water is going to have a polar side. One side of it, one pole of it is going to be different than the other side of it, okay? It has different parts with opposite electrical charges. Lots of covalent bonds are nonpolar, many, many, many. But because the shared electrons are equally distributed across the atoms that make it up. Not so with water. In water, they tend to hover more over to the oxygen side of the molecule, making water more negative pole at the oxygen pole and more positively poled at the hydrogen side. This explains why salt dissolves in water. If you look at this, here's water, that's great. It has a negative end and a sort of a positive end. These are micro charges, but they are there, okay? And the negative chloride from sodium chlorine is attracted to the positive ends of the water molecules that surround it. The positive sodium end of a sodium chloride is attracted to the oxygen ends that are more relatively negative that surround it. And so the sodium chloride compound will start to come apart in water and realign itself so that its negative ions are attracted to the positivity of the water molecules, and its positive ions, the sodium, will be attracted to the negative end, the oxygen side. And that's how it dissolves, okay? Any question about bonds so far? Okay. Let's talk a little bit more about water. This is the most abundant inorganic compound we have. We are about 2/3 of our body weight is water. 2/3 of all of us. That means if you weigh 170 pounds, 2/3 of you is 112 pounds. You are 112 pounds of water. How much does a gallon of water weigh? 8 pounds, roughly. Okay, that means if you are 112 pounds of water, if you're a 170-pound person, 112 pounds of water divided by 8 pounds per gallon, you are 14 gallons of water. Okay, that's what we are. I mean, think of a gallon jug of milk, 14 of those, that's you. Okay, we are mostly water. Okay. Water is important because it's a solvent. We already know that things will dissolve in it, like salt. It's a lubricant, and it changes temperature pretty slowly, which is nice if you're not a lizard, not a cold-blooded creature, because we need to maintain our temperature in a very narrow range for everything to work right. As a solvent, substances dissolve in water, right? Solutes. Those are the things that will dissolve in water. Glucose is dissolved in the water part of blood, our plasma, and it's transported to all of our cells. Saliva, which is a huge water content, helps dissolve some of our food substances, and it stimulates receptors in our taste buds on the tongue. Waste products that our body manufactures as part of living are dissolved in urine. It's mostly water, and it's excreted, okay? As a lubricant, it prevents friction. We have a big water component in our digestive tract. Swallowing depends on saliva. Slippery mucus secretions permits passage of food through your intestines. Joint fluid, synovial fluid, prevents friction in your joints as you move about, as you move your bones. And the fact that water changes temperature pretty slowly is good for us because it keeps our body's thermoregulation, our temperature regulation, in a narrow range. It absorbs a great deal of heat before the temperature starts to rise. Think about boiling water to make pasta. You turn on the stove and you and you're looking at this and it seems to take forever for it to start to boil. It takes time for that heat to change the temperature of the water until it reaches its vaporizing point and becomes boiling. And it has to lose a fair amount of heat before the temperature goes down. Take this thing off the stove, put it over here. It takes a long time for that water to cool off. That helps our bodies maintain a constant temperature. And it also, when it does evaporate, it takes a lot of heat with it, which is great because it cools us in a hot environment. When we sweat, it allows excess water to vaporize and it just takes the heat with it. So these are all really useful functions for a substance that makes up about 2/3 of our whole body composition. Where does the water live? Is it all in your blood? It's not. It's in different kind of compartments. 2/3 of us is water, and about 2/3 of that lives inside of our cells. It's called intracellular fluid. Okay, but that means 35% of our body water is out of the cells. Where is it? It's in our blood, in the plasma part, the fluid part of our blood. It's in our lymph, the water contained in our lymphatic system, our lymph vessels. It is interstitial water, which is in the small spaces between cells in our body. And it's in specialized fluid, like our joint fluid, our synovial fluid, our cerebrospinal fluid manufactured in your brain that circulates all the way down through your spine and back again to provide nutrients and stability to the environment of the brain and the nervous system. It's in your eyeballs, your aqueous humor, for example, okay? So if we weighed 170 and we were 2/3 water, that's 14 gallons of water, and then 2/3 of that lives in your cells, okay? So that's 9 gallons. And then just under 5 gallons lives outside of your cells in these kinds of places. We also have what are called trace elements. These are elements that our body needs, but in just small quantities. We need calcium. It provides bone strength. It helps with blood clotting. It's crucial for muscle contraction. We need phosphorus. It goes into bone, goes into teeth. It's part of your DNA and your RNA and in your cell membranes. Okay, it's crucial to our body's own energy manufacturing. We'll talk about that in a bit. We have iron. We need iron as the pigment that's in our hemoglobin that allows us to carry oxygen. It's in myoglobin, the pigment of our muscle cells. We need it for a function called cellular respiration, which is how we burn glucose and make energy. We need potassium for muscle contraction, for nerve transmission, nervous impulse transmission. We have copper, we have sulfur. So all of these things are just trace crumbs compared to the fact that 90%, 96% of us is hydrogen, oxygen, nitrogen, and carbon. And then these trace elements make up, and others make up the other 4% of us. All right, so let's regroup for a second. We talked about elements, we talked about atoms, we talked about how they combine by bonding to make molecules, right? Ionic bonds, covalent bonds, water bonds, right? Hydrogen bonds. And then we also talked about the very big role that water plays in human structures. Let's take a minute and look at how all these substances interact, okay? And they interact in the form of building and breaking down various molecules, various chemicals. So we're a chemistry factory. When chemicals interact with each other, they make new chemicals. There are two types. We can synthesize, we can build up and make new chemicals, or we can take something and break it into smaller parts, which is decomposition. So we can synthesize, make new, or we can decompose, break apart. Okay. So when two chemicals come together to make a new one, that's a synthesis reaction. This is a pretty common one. If a sodium ion were to interact to bond with a HCO3, a bicarbonate ion, positive, negative, this is an ionic bond and it forms sodium bicarbonate. There it is. Okay, it's bicarb. If we had a decomposition reaction, let's say we have hydrogen chloride. If this comes apart and ionizes into hydrogen ion and chloride ion, okay, then we have taken HCl and broken it apart. In this case, we've taken apart its ionic bond. So this is important to how the body works because we are constantly conducting vast numbers of synthesis and decomposition reactions just to stay alive, even if you're doing nothing. If you are asleep, this is all going on in the background. Let's think for a minute about how we make energy in our cells. This is called cellular respiration, okay? It's energy production within our cells. And it involves some component pieces. It involves the chemical glucose. It involves oxygen. And something happens when these are in the right circumstances, because then the glucose starts to come apart. And ultimately, this reaction produces CO2, another molecule, carbon dioxide. It produces H2O, water. And it produces something called ATP. And in the process, it gives off heat. So whatever this is going on in our cells all the time. You get glucose, you have oxygen, you're going to wind up with this, water, ATP, and heat. Okay. Here's the formulas. Here's a glucose molecule, C6H12O6. And in the presence of 6 molecules of oxygen, it will produce 6 molecules of carbon dioxide, 6 molecules of good old water here, and 36 molecules of whatever this is, adenosine triphosphate, and it liberates heat in the process. Okay, so basically, pay attention to the fact that you need to eat to get the glucose in, and you need to have functioning lungs to get the oxygen in. And look at how much one molecule of glucose produces in terms of carbon dioxide and in terms of this ATP stuff. So if everything's working right, one of these is going to give you 36 of those. That's pretty efficient. ATP is a big complex molecule that has 3 triphosphate, PO4, molecules dangling off the end of it. This is really important because this is our energy source. Okay, but this is a really efficient biochemical reaction. Now, oxygen is 21% of the atmosphere, at least currently, and it's 21% of the atmosphere if the atmosphere is not dense with smoke, for example. But it's essential for efficient cellular respiration. You need 6 of these to make one of these turn out to 36 of those. So we have to have it. And carbon dioxide is produced by the cells as it's a waste product. We got to get rid of that. We can't have that hanging around. We have to get rid of it as soon as it's produced to keep its levels in a biologically safe level. If it accumulates too much, it creates an acid. It converts to carbonic acid, which can kill your cells and tissues and ruin everything. So as good as this system is in producing all this ATP, it produces this byproduct of carbon dioxide, which we just have to get rid of somehow, okay? So we need to exhale this as quickly as we can. Those 6 carbon dioxides are a waste product for every 1 glucose we convert. And if we retain it, it'll cause all these fluids to become too acidic. So you could have a decreased gas exchange in your lungs, for example, if you had bad lung disease and you couldn't exhale your carbon dioxide that you're making just by being alive, that would start to accumulate and it would be converted into an acid and cause a condition called acidosis. Okay. So let's talk a little bit about acids and bases and figure out how we protect ourselves from swinging either too acidic or too alkaline. Okay. An acid's a compound that will break down and it will release hydrogen ions. Okay. And the strength of an acid, this is basic inorganic chemistry, the strength of an acid depends on how much hydrogen ion is in the solution. Okay. So if you had something like hydrochloric acid concentrate, there's a lot of hydrogen ion floating around, and that's a very acidic solution. The strength of the acid depends on the degree of dissociation or concentration of the hydrogen ions. A base dissociates into hydroxyl OH ions, and the strength of a base depends upon how much dissociation or OH concentration there is, or how much free, unprotected OH there is in the solution. Okay. The relative concentration of hydrogen ion or hydroxyl ion in a solution is measured on what's called a pH scale, parts hydrogen. So hydrogen is our focus. And it ranges from 0, which is unbearably acidic, to 14, which is very non-acidic. It's very basic, very alkaline, okay? 7's neutral. So anything less than 7 leans toward the acidic side, and anything more than 7 leans away from the acid side, more toward the alkaline side, the basic side. The issue with the pH scale is that a change of 1 unit results in it means there's a 10-fold difference in the concentration of the hydrogen ion. So it's a logarithmic scale. So instead of just being linear, it goes like this. It accelerates very quickly. So pure water has a neutral pH. It's right at 7, it's right down the middle. Anything lower is more acidic and anything higher is more alkaline. Here's some examples, okay? If we're right down the barrel, neutral, our saliva and even milk is a little bit more acidic than pure water. Tomatoes, grapes, think of everything that you taste that's tart is more and more acidic. Beer, vinegar, our hydrochloric acid that our stomach produces to start digesting food and protein, it's way down here. It's very acidic. The stomach has to be really smart organ to protect itself from being exposed to the acid that it's making to do its job. If we go in the other direction, blood is a little bit alkaline. The normal pH range of blood is between 7.35 and 7.45. Eggs are a little less acidic. Seawater is less acidic. Household bleach is a whole lot less acidic. Household pneumonia is very alkaline. And what used to be sodium hydroxide oven cleaner, which I don't even think they'll allow you to get anymore, Easy Off oven cleaner used to be very alkaline. It would coagulate your protein, your skin, on contact, which is why it burned everything off of your oven. Here's a little more on the pH scale. Lemon juice is pretty acidic. Coffee is acidic. Some people have trouble tolerating coffee because of the acid content in it. Saliva is a little bit acidic. Our intracellular fluid in the cells is a little acidic, which sort of makes sense because that's where all of our glucose metabolism takes place. All that carbon dioxide, 6 molecules, is being produced for every glucose, inside of our cells and is degrading into a little bit of a carbonic acid molecule. Blood lives in this range. This is normal pH for blood. Milk of magnesia, ammonia, these are way more alkaline. It would really be nice to have body systems in place in order to protect ourselves from wild swings in pH that could be toxic to our cellular biochemical reactions and basically destroy them, and we would die. We need something to buffer us against these wild swings, and they are called buffers. Okay. It's a chemical or a combination of chemicals that will either absorb excess hydrogen or release hydrogen so that it keeps the pH in this 735 to 745 balance. We use our kidneys, the renal system, to excrete excess acid in our urine. We use the respiratory system to exhale excess carbon dioxide that we are producing by our basic metabolic function of metabolizing glucose and making all that carbon dioxide. And we use a thing called the bicarbonate buffer system to chemically rid the body of any acids and keep us stable in this 735, 745 zone. Here's how it works. Carbonic acid is a very weak acid, and sodium bicarbonate, right, baking soda, is a very weak base. And these chemicals are present in all of our body fluids, but especially in our blood and our extracellular fluid, our fluid in our tissues, that 35%. Carbonic acid, H2CO3, will ionize into a hydrogen ion and a bicarbonate ion, a positive and a negative. Sodium bicarbonate, NaHCO3, ionizes into a sodium ion and the bicarbonate ion. And they work in this constant give and take relationship between carbonic acid and sodium bicarb to keep our pH in balance. Say, for example, we had a solution, okay, with this sodium bicarbonate buffer in it, and we added a strong acid. We added some hydrochloric acid into that. It'll produce a reaction with our buffer system so that the hydrochloric acid here will combine with the sodium bicarbonate in my buffer to produce sodium chloride and H2CO3, table salt, and the much weaker carbonic acid. So I've taken a very strong threatening acid and neutralized it pretty much and turned it into a weak carbonic acid. And that would only change the pH just slightly, preventing a big drop in the pH of my extracellular fluid. Okay. So we've effectively converted really strong hydrochloric acid into the much weaker carbonic acid. And we've maintained our overall pH in the safety zone of 735 to 745. So with this bicarbonate buffer system, we can take care of an acid load, right? We can convert it into a weak acid and preserve our pH. If we wound up in a similar situation with a base, if we added sodium hydroxide, then it would combine with my carbonic acid and become H2O. We get water, and we get sodium bicarbonate. So that's sort of nice because we regenerate the bicarbonate buffer that way. We get water, which we can always use. And this will prevent a drastic change in pH in the positive direction, in the plus 7, 8, 9, 10 direction that this strong base would otherwise cause. So it prevents a drastic change in the pH by buffering us against a strong alkaline, a strong base. So there's this constant chemical give and take, this consumption and replenishment of sodium bicarbonate and carbonic acid. And this goes on inside of us all the time, okay? We don't sense it, we don't know it, It's built there in the background, and it just takes care of itself. So these are constant reactions. Acids will react with weak bicarbonate base to form a weaker carbonic acid and sodium chloride. Bases will react with a weak carbonic acid to form weaker bicarbonate base and water. So we tend to keep ourselves in this 735, 745 zone. We tend to run a little bit on the acidic side. Our body metabolism tends to generate acid. And so we need to buffer these acids more frequently to keep the pH normal for us. And so we need more sodium bicarbonate than we need carbonic acid, because we are buffering acids all the time, and we buffer them with the bicarb. In fact, the ratio of these buffers is 20-1, sodium bicarbonate to carbonic acid. So somehow the body knows that we are going to be producing acid as part of our metabolism, but we've got a system in place that's 20 times richer than having to take care of bases, and we can take care of that if all systems are working properly. Let's talk a little bit about salts. It's pretty fresh for us with sodium chloride. These are inorganic compounds, right? They're positive and negative ions. And we call them electrolytes because the ions that make up these salts are electrically charged, right? Positive ions, negative ions. And the most important salts in our body contain sodium, potassium, calcium, okay? And so we need those as well. So far, all we have been talking about are inorganic parts of us. Okay, the sodium, the chloride, the hydrogen, the oxygen, this sort of stuff. We have not been dealing with anything that makes us organic. And what makes us organic is that all of our organic compounds always contain carbon and hydrogen, and usually they have oxygen as well, but not always. And our major organic compounds include things like our carbohydrates, our lipids or fats, our proteins, and our nucleic acid. So if we're going to really understand how the body does what it does, we need to know a little bit about carbs and lipids, and especially protein as well. For us in the EMS world and in the day-to-day physician world, these are the four major categories that we need to understand. So let's start with carbohydrates. Carbohydrates are made up of carbon, hydrogen, and oxygen. And the ratio of hydrogen to carbon is 2-1. So in a carbohydrate, for every carbon, there are 2 hydrogens. So if it has 4 carbons, it's going to have 8 hydrogens, okay? This is the primary source of energy for our body cells, okay? And we classify them according to their molecular size, their complexity. A monosaccharide, single sugar, like glucose or fructose or ribose, those are the monosaccharide types, one sugar type of molecule. If I take 2 monosaccharides and stick them together and make a disaccharide, 2, then I've created a different carbohydrate. I've created a disaccharide, a maltose, a sucrose, lactose, the sugars in milk and dairy products. Sucrose, you'll see in many things that we eat. These are all disaccharides. 2 monosaccharides fused together. And sometimes we have a string of monosaccharides stuck together into a smaller chain. Oligo means few, means smaller. So we have oligosaccharides, okay? We see those are often markers on our cells, antigens on our cells that serve specific purposes. And then we have gigantic, complicated carbohydrate molecules called polysaccharides. Okay, many, hundreds. Okay, starches, glycogen, which is a huge, complicated chain of glucose molecules all strung together. But these are the substrates of what we burn for our fuel. Remember that equation earlier that showed 1 molecule of glucose making 36 molecules of ATP? It's the carbs. The carbohydrates are converted into glucose, that key entry ingredient into the equation, the glucose. So monosaccharides are single sugar compounds, glucose, fructose, galactose. The physical arrangement differs for each one. They each have a different shape. But the liver can take any one of those and rebuild it into the glucose molecule structure so that our cells can use it to manufacture all that ATP stuff. So the liver is sort of like it's like a conversion factory for carbohydrates. It can take them in their simplest molecular form and construct them into glucose, which is exactly what we need to get things where they need to go. So here's glucose, our C6H12O6, right? Monosaccharide, one sugar, it's one molecule. Disaccharides are double sugars, right? Made up of 2 monosaccharides linked together and can be digested into monosaccharides and then used for our energy production. So when they fuse together, here's glucose and here's fructose, 2 monosaccharides. If I'm going to synthesize them, right, build them into a new molecule, we go through a process called dehydration synthesis. Dehydration means to take out water. We're going to take a hydrogen off of one end of this fructose molecule. We're going to take an OH from another end of the glucose molecule and dehydrate them and build water. And now I'm going to result in a covalent bond of these 2 sugar molecules, converting it into a disaccharide, converting it into sucrose. Okay? The oligosaccharides, as I said, are relatively small. They have maybe up to 30 monosaccharides stuck together. It's relatively few in the chain. And we find those on the outer surfaces of our cell membranes. A polysaccharide has lots. I mean, lots, hundreds, thousands of monosaccharides linked together. They're very big molecules. They're long chains. We also call them starches in the common language. Polysaccharide, many sugars stuck together. Thousands of glucose molecules, such as starches, like that. You eat this stuff, and you can turn it into glucose molecules. Now, glycogen, excuse me, glycogen is a special kind of a polysaccharide. It's a highly branched chain of glucose molecules all stuck together. It's like a fuel depot of glucose. So after you eat a meal that has carbohydrates in it, your blood sugar goes up, right? And your glucose that is now being digested, we've converted all this stuff into glucose. We use it to build out ATP. And if there's excess, we stash it away for later. We build out a complicated molecule, right, called glycogen. And we store it in the liver, and we store it in our muscles. And then when we need it, we can convert it back into glucose and push it into the entry part of the equation and make more ATP. This is why you don't faint between your last meal and your next meal. Because if your body's working right and your liver's working right, you stashed away a whole bunch of glucose molecules in the form of glycogen. And when your glucose level starts to fall because you're not eating 100% of the time and you're metabolizing all your glucose, you just pull some out of the glycogen storage bank and fuel the equation, okay? So this is why you don't faint between your last meal, between when we started at 8 o'clock and when you're gonna have lunch after I'm done. You have to listen to me, or your next snack during break. People will do carbohydrate loading before they run a marathon, okay? We store up the glycogen in our muscles so that we can burn those sugars when we need them, like between mile 20 and 26, for example, of a marathon. according to the Mayo Clinic, if you're running a marathon, if you're exercising like that, after about the first 90 minutes of continuous exercise, you may use up your normal stores of glycogen. And this brings up the idea of carbohydrate loading before you run an endurance race. Because you want to have enough stashed away in your muscles and in your liver so that after 90 minutes, you're not going to collapse, or at least you'll be able to replenish your glucose with oral intake during the course of the race. But they say to carb load, maybe about a week before a marathon, you should try to increase your percentage of your calories to about half your total caloric intake. That's a lot. And then about 3 days before the event, they recommend that you increase that to about 70% of your oral intake. So you're really just packing in glucose that you're not using for routine activities, and you have a big storehouse full of it. And then about the week before the marathon, you should start tapering or decreasing your mileage so that you can keep your bank full, so that you can run 26 miles, and then draw on your grown, fully packed glycogen stash, without basically overeating all the time. So here's a representation of a glycogen molecule with about 30,000 glucose units in it. There's another carbohydrate out there called cellulose. This is a straight chain of glucose molecules that's produced by plant cells. And they use this in the structure of their cell walls. Okay? We don't have any enzyme that can digest this. We can't break this down with our bodies as good as we are. We can't. This goes through your GI tract, your gastrointestinal system, unchanged. This is also called fiber, okay? And it produces bulk. Because you can't digest it. It's not going to be broken down and absorbed into your circulation. It's just going to just hang out in your intestinal tract. And because you can't digest it, it adds bulk to your GI content, and it promotes efficient peristalsis. It gives your colon exercise to be able to sense that it needs to evacuate itself. So it's an important component, but we can't use it for anything other than the mechanics of it. Let's talk about lipids, okay? Lipids come in a couple of forms. They're either solid or liquid forms. They are fats, and they also contain carbon, hydrogen, and oxygen atoms, but their orientation is different than for carbohydrates. Most of these are not soluble in water. So it sort of asks the question, how do we carry these things around in our blood? Because our plasma is, water. How do we do that? We'll talk about that in a little bit. They need a special transport molecule to hold on to them so that they can be carried through your circulatory system. So our fats are storage forms for excess food, okay, or stored energy. So excess nutrients, excess calories that we're not using to produce energy and do all of our chemical reactions, those are stored as fat in our body's adipose tissue. It doesn't matter how lean you are on the outside, all of us have fat, and we need it because some of that fat content is protective. It cushions vital organs like your eyes. There's periorbital fat. There's perirenal fat, fat around your kidneys. There's pericardial fat. Okay, so we need some of this stuff. In a pinch, the liver can convert fats and even protein back into glucose. If you think of a fasting situation, or much worse, a starvation situation, we will start to consume body fat, and the liver will convert it into a different form of a organic compound will convert it back into a carbohydrate and into glucose so that we can sustain ourselves. The fat structure is a kind of a variation on a common theme. It consists of fatty acids, which are carbon-hydrogen chain, and a 3-carbon chain called glycerol. Okay. A fatty acid is a long chain of carbons with, on one end, there's a thing called a carboxylic acid group. Okay, on one end. If all the carbons are bonded together with one pair of electrons being shared, that's called a saturated fat, saturated fatty acid. If they're double bonded, they're sharing 2 pairs, that's called an unsaturated fat. Okay, this one is polyunsaturated. It's got a bunch of them. So if we keep in mind that this is a 3-carbon anchor, and we're going to attach to it various fatty acids, you can almost think of it as a large capital letter E, with the vertical line being the glycerol, and then the fatty acid branches coming off and being the short legs of the capital letter E. So a triglyceride has a glycerol molecule and 3 fatty acids coming off of it. It is a really concentrated source of energy because excess nutrients that we're not burning are either stored as glycogen or they're stored as fat in fatty tissue. Saturated fats, these tend to be found from animal sources. Unsaturated fats with the double carbon bonds tend to be found in plant sources. Okay. So these are derived from fats that either we eat or we can make them from other energy sources like carbohydrates. They have carbon, hydrogen, and oxygen in it, and we can synthesize those. So things that we ingest in a meal that were not used right away by our tissues can be converted to triglycerides and transported into our fat cells and stored there. And if we have excess triglycerides in our blood, in our plasma, that's been linked to the occurrence of coronary artery disease in some people. So when we start talking about medications that your patients may be on that you see, they may be on medicines that lower their fats, lower their triglycerides. So even if they can't tell you stuff and they have symptoms, if you go to their medications and you see a drug like Lipitor or one of the other statin drugs, you can make an assumption that cholesterol, triglycerides, fats are an issue for this person and store that in your brain while you're continuing your workup. So a triglyceride has the glycerol molecule, 3 fatty acids. This one has 2 of the fatty acids are saturated, and it has 1 unsaturated fatty acid. Okay. It's got the double bond here. Then there's a thing called a phospholipid. Okay. It's similar to a triglyceride, except one of the fatty acids actually is replaced with a phosphate, with a PO4. These are not stored as fat energy. These are structural components of our cells that we need. Phospholipid lecithin makes up the membranes of our cells. If we didn't have this particular lipid, our cellular structure would just open up and fall apart. So this is crucial. Myelin is like the insulation over a copper wire. Okay, it facilitates conduction through our nerves. And there are diseases where the myelin sheath is deteriorating, called a demyelinating disease. And we think, for example, that multiple sclerosis is a demyelinating condition. So we need these things. They're not just, bad fats. Some of these are critical things that we have to have. So rather than being stored as forms of energy, the phospholipids are structural components of our cells. So that would look something like this. This is a saturated fatty acid. That's one of them. Here's an unsaturated one, and here's a phospho fatty acid. So this is a phospholipid. Okay. We talked about how our blood can carry these things, because if you put fat in water, it doesn't dissolve, right? It just floats. If you think of a water-based acid like vinegar and salad oil, olive oil, if you don't shake that stuff up, they separate. The oil floats on top of the water-based vinegar. Same things would happen if you put this in your blood. And so how do we get them transported through our mostly watery blood? It turns out that these fats have a water liking and a water not liking end. And in water, these lipids align themselves so that the water liking, the hydrophilic, I like this, heads face the polar end of the water molecules. And it leaves their hydrophobic tails stuck deep into the water droplets. So they basically orient themselves so that they're surrounded by water, and they take advantage of the fact that water is a polar molecule. And the fats orient themselves so that the part that likes the water molecule faces the polar end of the water molecule. These are called micelles, okay? Micelles form spontaneously in water. It's essential for the absorption of our fats or fat-like substances, because otherwise we couldn't carry them. They would just glob into the water of our plasma. We have certain vitamins that we need, and some of them are fat soluble. And if we don't have ways to carry them, we can't distribute them throughout our body. Bile is formed in the liver and secreted by the gallbladder, and that allows micelles to form. So now we have something that's made in the liver that's excreted into the GI tract that will hold on to fats so that we can get them into our body and distribute them all over the place without having globs of fat clogging up our pipes. Okay. All right. Now that takes care of carbohydrates, and it takes care of lipids. Steroids have 4 carbon rings in their structure. Okay. Cholesterol is the most important steroid. Everybody thinks cholesterol is like, no, terrible, I don't want to talk about it. We need this stuff. It combines with phospholipids, right? Glycerol with 3 chains, one of them having phosphates in it. It stabilizes our cell membranes. It's the raw material for the synthesis of our hormones. In the presence of sunlight, we can change it to vitamin D, which we need for bone strength. And the liver makes those bile salts that help us transport fats in our blood from the cholesterol base molecule. It looks like this. It's a 4 carbon ring structure. 3 of the carbon rings have 6 carbons, and 1 is a 5 carbon. Okay, here's the molecule. And it's sort of whatever's going on here is the defining piece. Okay. They all share this 4 complex ring, and then they differ in their side chains that attach to the carbon rings. So this is what cholesterol looks like. Testosterone and estrogen have similar structures, but they have different side chains. And then we have the steroids, the anti-inflammatory steroids, for example. So testosterone-like steroids are muscle-building steroids, which is why the sports franchises have banned this stuff, because it puts athletes at an unfair advantage over other athletes who are playing clean. But we have anti-inflammatory steroids as well. Our body makes cortisol, part of our normal functioning. It's an anti-inflammatory steroid. It's a steroid that peaks as we wake up. It sort of it sparks the day for chemical reactions in our body. And then it tapers off over nighttime, and then it peaks again in the morning. So it sort of runs this kind of a cycle. Cortisone, which you can buy a cream of over the counter, looks like this. It's this basic cholesterol molecule. Here's the side chains that make it do what it does. And if in the lab, somebody took this and converted this into a double bond, they've taken cortisone and made prednisone, which is a way more powerful anti-inflammatory medication. This one change increases the potency of the molecule 5 times. And then there are other changes that can make even stronger anti-inflammatory immunosuppressive steroids that are used to treat various diseases or profound allergic reactions or reduce brain swelling or these sorts of things. A cardiology colleague of mine told me that she does not know a physician over the age of 40 who is not taking a cholesterol lowering medication preventively to keep their lipids low and in balance. So it tells you that there's a defined important role of keeping your triglycerides, for example, and some of your cholesterol components in a lower zone because they are associated with the formation of arterial sclerotic changes in the linings of your arteries. And if they're left untreated, unattended to dietarily or whatever, we make this stuff. Some people are genetically built so they make a lot of it, no matter what they do with their diet. And they need medical help to lower these things into a safer zone so that they don't wind up with damage to the linings of their arteries that feed their heart, feed everything else, strokes, all of that stuff. So it's something that should be looked at. Many people recommend that you have your lipid profile, your cholesterol and triglycerides checked when you're probably 30 years old, just to see where you are. You can modify a lot of this with diet and exercise, but since we synthesize this, some of our bodies are wired to synthesize more than we need, and we can try to mitigate this so we don't wind up with long-term changes. Okay. Let's talk a little bit about proteins. So we talked about carbs, we talked about lipids, we talked about steroids, we're going to talk about proteins. Proteins are monstrously large molecules, and they're made up of only 20 basic building blocks, 20 basic units. And those building blocks are called amino acids. Okay. And these 20 are made up of carbon, hydrogen, oxygen, like all the other organic stuff, but they also have a nitrogen element in there as well. Okay. And they can have between 50 and hundreds of thousands of amino acids strung together to build each specific protein. So you could imagine what would happen is if you didn't have an adequate protein intake in your body. The amino acids come from what we build ourselves, but there are 9 of those 20 that we can't make. So we have to get it in our foods, okay? Which is fine because by and large in this country, by and large, there's enough available to us that we can get all of them. So our body's building machinery has all of its basic building block units, okay? Vegetarians can get them all, even if you don't get your protein from meat sources, okay? You can get them all. But these are the most abundant and diverse compounds we have in our bodies, okay? if you don't do anything at all, if you're a 170-pound person, you'd need about 60 grams a day of protein. And if you're lighter, if you're 120 pounds, you'd need maybe 45, something like that. It's not hard to get this stuff. A cup of milk has 9. If you wind up with a single serving of Greek yogurt, you can get 15 or 17. You get it from beans, you can get it from tofu. Tofu is rich in it, like 10 grams for half a cup. If you eat canned tuna, you can get another 10 or 11. Salmon, even veggie burgers, which are all vegetable, can have 10 or 11. Sometimes they're higher protein depending on the content of the vegetable protein they put in there. Peanut butter. Standard serving is a tablespoon. There's 7 grams of protein in there. An egg has 6. So it's hard if you're eating a balanced diet. It's hard not to get what you need just to have the protein that can be converted into all of these amino acid building blocks. And you have all your basic ingredients to make all the hundreds of thousands of proteins that we need. The basic amino acid structure looks like this. It's got a carbon, and on one end it's got, it has 4 binding sites. Carbon can take, 4 pairs of electrons. One can come out of hydrogen. One is a carboxylic acid group. Okay. Another has an amino group. There's a nitrogen. And then the thing that defines which amino acid it is, in this graphic, it's called an R group. This is the one that tells you what amino acid you're dealing with, because they all have these 3 components on their edges. It's this one that tells you whether you are leucine or some other amino acid, okay? And they bond together. They bond with each other to make these massively long chains. Take a look at this picture again. We just talked about it when we were talking about dehydration synthesis of monosaccharides to make disaccharides, or in many cases, polysaccharides, right? Where and hydrogen comes off of one building block, in this case, fructose, combines with an OH from the other building block, glucose, and makes a disaccharide bond, right? It's not too different when you talk about how the amino acids build their bonds. Here's an amino acid, glycine. Here's its carbon. Here's its carboxylic acid group, its amino group, its hydrogen, and its defining property on its 4th bond is a hydrogen ion. Here's alanine, another amino acid. Its defining group is a methyl group, CH3. If these 2 decide that they're told to bond together, they also undergo a dehydration synthesis and produce water. And we now have 2 amino acids bonded together, and that's called a peptide bond. So we wind up with a covalent bond of a couple amino acids. That's 2. Remember, we said that you could have hundreds of thousands of these things going on in any one given protein. And so there's a lot happening here to get the right amino acids in the right order to build a certain specific protein. So these might be 9 different amino acids in an exact sequence. They're all linked with peptide bonds. This is a polypeptide. It's got a bunch of these bonds. And they can take on all kinds of goofy shapes. They can be swirls or cylindrical. They can be almost pleat-like. So the geometry of how these things are bonded can also change, because look what's happened here. These are all singular. These are on top of each other. These are held together themselves and also with a bridge. So they can get very complicated. It's the precise sequencing and ordering of these amino acids in the polypeptide that determine exactly what the protein is and what it's supposed to do. And if you change one of these, if I substitute an A8 for A7, so I have 1, 2, 3, 4, 5, 6, 7, 7 amino acids, and A9, this protein is going to be a different protein. It won't do what you thought it was supposed to do if they were all different ones in this order. So there's a lot of room for messing this up. And it's remarkable that in most cases, they work just fine. But changing even one amino acid in a sequence of tens of thousands changes the protein, and it may render it incapable of performing its normal function. So it's just one of the other miracles that we have to consider when we're trying to figure out how the human body works. Here's different protein structures. Myoglobin, which is the protein of your muscle cells that carries the sort of reddish pigment of muscle, looks like that. This glob is the protein structure of hemoglobin. This is the protein structure of keratin. It's in your hair, your fingernails. It's a very fixed structure. So these three-dimensional twists and turns can get pretty complex, and some of them are very, very tough to come apart, which is good for if they're structural proteins, like a tendon or something. But some of them are very busy making and doing other things, and so they're very functional. So functional proteins are less stable because their three-dimensional shape is held together by weak hydrogen bonds. And you know that those are the weakest of the bonds that we have, but they do incredibly neat stuff. They're very important. We find them in hormones, growth factors, enzymes, our hemoglobin, antibodies. They're very critical to the functioning of the human body. Structural proteins form essential body parts: ligaments, tendons, collagen, our connective tissue. It's pretty firm. Keratin, they're very stable. So some are designed as scaffolding for what our body needs to be able to work, and some are the production part of what we need to do. We have enzymes, that digest things and break things apart and stuff. Those are very specialized proteins. They're proteins that make other chemical reactions to make other proteins, for example. And there's a thing called an active site theory. And what that means is that the pieces of the building blocks that the enzyme is going to work on fit into specific sites of the enzyme so that the enzyme protein can manipulate them to build whatever it's supposed to build. I'll give you an example. Here's a schematic. Here's an enzyme. This is a protein. It's taking these two building blocks. It's got active binding sites on it that mirror the configuration of the building blocks. So this piece goes here, this piece goes here. The enzyme protein causes the chemical reaction for these two pieces to fuse together and bond. We have now made a new synthesis. We've synthesized a new product. Off you go. My binding sites are open for business. Bring me the next pair. Okay, so it's like an assembly line. So these are really important, and it's important that they're built to the specifications that they need so that they can do what they're cut out to do. If they're defective, you may have an abnormality. They may not work properly, they may work less efficiently, they may not work at all, and then you have a body organ that's not able to function optimally or very well at all, and that causes illness. Remember, there are 9 amino acids we have to eat. The rest of them we can build from the component pieces we need for carbon, hydrogen, oxygen, and nitrogen to actually build those amino acids. But 9 of them we have to get from oral sources. Okay, there's one more organic compound that we need to talk about. And it's that. It's the nucleotide. The nucleotide's kind of complicated, but all of them have 3 parts. They have something called a nitrogenous base, nitrogenous base, attached to a sugar molecule, attached to a phosphate, PO4. This makes a nucleotide. So the sugars are ribose, the phosphate group is phosphate. It's this that makes a nucleotide what it is. And we have different ones of these, different nitrogenous bases, okay? Here they are. 1, 2, 3, 4, there's 5, okay? Adenine, guanine, cytosine, thymine, and uracil, okay? These are the 5 nitrogenous bases that we have in our nucleotides. Okay. They're grouped. Some are called purines, there's 2 of those, and some are called pyrimidines, there's 3 of those. Okay. When the nucleotides are arranged in a specific order, in different combinations, they produce unique sequences and twists and turns called nucleic acids. So here is a chain of a base, a sugar, a phosphate, bonded to another base, sugar, phosphate. See, the bases are different, right? So these nucleotides consist of different bases, you know, one of the 5, the sugar and the phosphate, and they're in a specific order, okay? The 2 main nucleic acids that we have are DNA, deoxyribonucleic acid, and RNA, ribonucleic acid. So if we think of one single human cell, okay, and we go way into the core of the cell, here's the cell membrane, right? That's got a phospholipid in it to give it structure. There's a bunch of stuff out here in the cytoplasm, right, in the gel. And then there's a nucleus. Inside the nucleus is an owner's guide. It's an instruction manual that tells the cell what proteins it's supposed to be making. Okay. This is where the DNA lives. And the DNA lives in our chromosomes. Each chromosome is made up of DNA that's tightly coiled many times around proteins. This is the blueprint for what the cell is supposed to be doing. Here's the DNA. It's all coiled up. Every cell in the body has the same DNA. It's inherited from the single fertilized egg of the parents, right? The DNA is all tightly wound up and coiled and coiled and coiled, tiny, tiny, into these chromosomes, okay? How tightly? If all the DNA in your body was unraveled and put end to end so that this DNA and this DNA and this DNA were all lined up together, it would reach the sun and back 600 times. Put another way, all the DNA in all your cells put together would be about twice the diameter of our solar system. This is really tightly wound up stuff, okay? The segments of the DNA are made up of these nucleotides, the nitrogenous base, the sugar, and the phosphate, in a very specific order. The specific order, these segments, are our genes. Those ordered nucleotides, these ordered segments, are a template. They're the instructions. They are a code for the precise order of the nucleotides in the DNA segment that's responsible for the assembly of the amino acids into a specific polypeptide protein. You make a protein, you're going to make a protein, you make proteins. Remember, we have 100,000 different proteins. We have 20,000 to 25,000 genes telling us what to do. So the DNA controls our inherited characteristics, our eye color, our hair color, our blood type, and it's our DNA that makes each of us so unique. But the DNA also codes the information needed to make every one of the many thousands of proteins and enzymes in our body. It controls the creation and the destruction of our lipids, our carbohydrates, the synthesis reactions of our enzymes involved in building all of these things. So the segment of DNA that codes for a specific protein is based on the exact order of the nucleotide contained within that segment is called a gene. And it's that exact order that directs how individual amino acids are supposed to be bonded together to make every single protein we have. All of us, every human in our species, we are 99.9% identical in our genetic makeup. That means we only differ from each other by the remaining 1/10 of 1%. Most of our DNA determines that we are human, rather than determining how we're different from each other. Your DNA sameness tells you that you are all human beings. And since 96% of all of us is carbon, hydrogen, oxygen, and nitrogen, as different as we might appear, we are really very much the same. Speaking philosophically, it's astounding how much alike we are. Speaking physiologically and biochemically, what a gift to those of us who deal with people who are ill, that we are so much the same, because all of our bodily physiology functions are pretty much contained in the sameness of our DNA. So it's very convenient for those of us who see people who are struggling with some abnormal function of their body, that we're built pretty much identically in terms of what those bodily organs are supposed to do. And it helps us to be able to formulate what went wrong, why are these symptoms here, what's happening to them in their cells that's making this so bad. And when you go to the drug box, you can figure out what it is you're supposed to be doing to sort of shift things back into their normal pH, protein synthesis, acid-base status, temperature regulation, oxygen availability, all of the substrates we need, our amino acids, all of that stuff, to get people back on the best track you can get them on. So DNA is our deoxyribonucleic acid. It carries the genetic information of the cell and has tens of thousands of genes, many segments of nucleotides. And each gene is the recipe on how to build one specific protein molecule. And since there are 20 to 25,000 protein coding genes, and the genes themselves are made up of varying lengths of nucleotides, there's a huge amount of complexity going on here, and you might guess there's a lot of room for mistakes, something to go wrong. So we always use adenine, thymine, guanine, and cytosine. Two strands of the nucleotides called a double helix twist around each other. It's like someone took a ladder and torqued it. It comprises the hereditary portion of our chromosomes in the nucleus, and it's controlled by the sequencing of these bases, the adenine, thymine, cytosine, and guanine, to tell us what we're supposed to be doing, organ by organ, cell by cell. In DNA, adenine always pairs up with thymine, those two bases, those two nucleotides. And guanine always pairs up with cytosine, okay? How each cell knows that it's only supposed to make the proteins that are specific to what that cell's supposed to do has been a puzzle for many, many years. If all our DNAs are inherited and they all are supposed to be making all these different proteins, how does your kidney know that it's only supposed to make kidney proteins and not muscle proteins? This has been a mystery for a long time. So we've got this DNA strand, adenine connects to thymine, guanine, cytosine, adenine, thymine. So they match up with a complementary pair, and they're held together by the weakest of bonds we've got, hydrogen bonds, okay? I'm going to show you a letter to a 12-year-old boy. In March of 1953, this man wrote a letter to his 12-year-old son who was away at a boarding school. Either this was customary to what they did in those days, or he was a bad kid and they sent him away to a boarding school, or something. Dear Michael, Jim Watson and I have probably made a most important discovery. We have built a model for the structure of the deoxyribonucleic acid. And he goes on to write to his boy in March of 53. You may remember, listen, he's talking to a 12-year-old, that the genes of the chromosome are made up of proteins and DNA. Our structure is very beautiful. It can be thought of as a long chain with flat bits of bases sticking out. Long chain with bases sticking out. And then he goes on to write the formula, and then he describes two chains wound around each other with a sugar and a phosphate on the outside and the bases on the inside of the chain. Then he draws the double helix with the specifics of certain bases needing to pair up with their complementary bases. Adenine with thymine, cytosine with guanine. And key is if the order of one chain is fixed, you know what the order of the other chain is going to be, because adenine always has to pair with thymine, and guanine always has to pair with cytosine. Okay. So if you know the bases on one limb of this double helix, then you'll know the partner base on the other side. So he said, if they're lined up like this, you know it's going to be on the other side. That's how it works. And then he says it's like a code. Okay? If you know one side, you're going to know the other side. And then he says, this is how nature makes copies of the genes. You unwind part of one strand and expose its bases, the adenine, cytosine, thymine, and guanine, and then you can see what the basis of its complementary side is going to look like. What its gene will look like. It's the order of the bases that make one gene different from another. We think we have found the basic copying mechanism by which life comes from life. And then he says, I have to get a letter off to Nature, which was one of the premier scientific journals of its day, which is now, there are so many different discoveries that have been made since 1953 that Nature has a biology, a microbiology, a physiology. They're like specialty Nature journals. But this was the parent of them. Then he says, read this carefully so that you understand it. And when you come home, we will show you the model. Lots of love, Daddy. Who is this guy? Francis Crick of the Watson and Crick model of DNA. So with James Watson and Maurice Wilkins, they discovered DNA base structure in the double helix model, and they were granted the Nobel Prize in 1962. This is what we are all about. This letter, his handwritten letter, was auctioned off in April of 2013 for $5.3 million. Wouldn't you like to have this hanging in your living room somewhere? Yeah, what's that? Well, it's the letter of the person who actually discovered DNA that he wrote to his 12-year-old. The heirs sold this letter at an auction to benefit scientific research. Half the proceeds went to the Salk Institute for Biological Studies in La Jolla, where Crick was a professor. Another 20% went to the new Francis Crick Institute in London, which is a medical research institute that opened in 2016. I'm sure Christie's auction house took a piece, but I don't know who bought it. It would be really interesting to find that out. So this is how it all worked: adenine, cytosine, thymine, and guanine. And we always thought this is how it works. If I see one, I'm going to know the other until April 23rd of 2018, things got more complicated. Two researchers in Sydney, Australia, published in Nature Chemistry, right, one of the specialty Nature journals, that they had discovered a thing called an I motif, which is a specific folding of the cytosine segment in a structure. Here's the molecule, and then the cytosine folded over on itself. And then it paired with another cytosine instead of guanine. And when they started looking for these, they found a lot of them. And they didn't know what they were looking at. And they wondered if it was an over or an under expression of a component of a nearby gene. We don't know. So just when you think you mastered something, somebody comes along and finds something else, and it kind of reshapes your knowledge base and your thinking. It doesn't necessarily unravel everything that you've learned, but it adds another dimension, another detail. And this is I can tell you from experience, much changed from the time I graduated medical school until later years when I was practicing. The same is going to happen to you. The ACLS standards changed a couple of times during my career. It may change again. There may be another drug that you're going to be using. So the point of this is that we learn and we master the best that we've got available to us at the time we're studying it, but it can't end there, because things change, they evolve, and we need to be able to reintegrate those into our understanding of why and how bodies do what they do and how diseases express themselves. So as hard as this is going to be to get through and learn all this stuff and say, I've got it, especially after you're practicing paramedics for a year or so, and you can recognize things really quickly and distill what you've got before you, something will change. A therapy will change. They may change the way you report stuff. They may change your documentation. All these little things are going to kind of disrupt your normalcy of patterning and anticipate it and be unhappy about some of it because it changes what you have to do, maybe documentation wise, but be on top of it because it'll augment your understanding of all you went to school for. So that's the DNA part. What about the RNA part? The ribonucleic acid. RNA is a single strand of nucleotides. It's one strip. And it synthesizes proteins following the information that the DNA told it to do. It uses adenine, guanine, cytosine, but it substitutes uracil for thymine, okay? And we think that the uracil makes it more stable as the RNA takes the information and brings it to the assembly line to start building proteins. We have triplets of specific bases, they're called codons, that will help code for a specific amino acid. Once I get that specific amino acid from the DNA and put it in place, then the RNA will tell me what acid I have to bring next to start assembling this protein. So a segment of DNA separates the weak hydrogen bonds, it sort of unravels, and it exposes the double helix and allows the RNA to pair up and copy the DNA's nucleotide sequence on that specific segment, okay? So on this piece of gene of DNA that goes from here to the sun and back, okay? This piece of gene, when it is exposed, it allows RNA to look at that and say, okay, you've got these 3 nucleotides here. I'm taking the information, I know what I need to do, and I'm going to take that out of the nucleus. And I'm going to go into the cytoplasm to a place called the ribosome. And the ribosome is the amino acid assembly factory. And I'm going to take this information, this recipe that the DNA gave me, and carry it out and deliver it to the ribosome and say, start putting together this amino acid. Get that amino acid, okay? So it makes a mirror imprint of the order or the sequence of the nucleotides in the order that they appeared on that DNA segment. But it replaces thymine with uracil, okay? The RNA takes that information out of the nucleus, goes to the ribosome, and it reassembles the nucleotides in their complementary partners. Adenine, uracil, cytosine, guanine. The DNA never leaves the nucleus, okay? And the order of the nucleotides codes for specific amino acids, and the exact order is instructed by that little segment of the DNA. So here's this big DNA thing. Here's a teeny little segment. It opens up, unfolds, and RNA takes the message. It's called messenger RNA. It takes that information and it leaves the nucleus and goes out into the real world. And it says, I know what amino acids I need to take to the ribosome. I've got the information. And then another piece of RNA called transfer RNA brings that to the ribosome, and we start building the protein. So DNA tells the RNA how to sequence the amino acids into these gigantic polypeptide proteins. If something goes wrong, and even one amino acid is encoded incorrectly, the protein may malfunction or not function at all. So here's a question. All of our cells contain the same DNA, right? I mean, it's our DNA. How does the kidney cell know that it's only supposed to make kidney functioning proteins and not cardiac functioning proteins or muscle functioning proteins? How does it know that? Well, it turns out that two scientists, Gary Ruvkun, who's a genetics professor at Harvard, and actually a graduate of Berkeley, and Victor Ambros of the University of Massachusetts, who went to MIT, these two scientists discovered another form of RNA called microRNA. And they discovered this in 1993. And it didn't mean very much to anybody. But it turns out that this microRNA acts as a regulator, and it switches off, or significantly at least suppresses, the protein synthesis mechanisms, which, remember, your DNA can make hundreds of thousands of proteins, and we only want it to make kidney proteins, okay? So what it does is it significantly switches off, it tamps down messenger RNA's ability to take all the information and make all kinds of crazy proteins, and it only shapes it to say, look, we could make hundreds of thousands of proteins. We need to make this many specific ones for the kidney. Let's make those, okay? So it inhibits the translation of all these amino acids that could make all kinds of crazy proteins that the kidney doesn't need, so that it can only select for the proteins it does need. It's what makes the kidney the kidney. It's what makes the muscle the muscle, okay? This marked messenger RNA is prevented from producing specific proteins so that it facilitates the types of proteins that we need for a certain organ to do what it's supposed to do. It selects for the production of proteins that a given cell needs, a muscle cell needs, a cardiac cell. This differentiates the proteins that are the key ingredients of different types of cells from the total number of the galaxy of proteins that the DNA gene might be able to code for. This determines how each organ does what it does in order to function as that organ in the human body. So Doctors Ruvkun and Ambros were awarded the Nobel Prize 2 months ago for this discovery, the Nobel Prize for Medicine and Physiology. This is really unbelievably sophisticated stuff, because it takes the fundamental understanding that all of our DNA can make all of the proteins in our whole hundreds of thousands of proteins, and yet each organ functions as its own organ. Each tissue is its own reservoir of what it's supposed to do. And so it selects for those by suppressing the production of all the others. Pretty amazing stuff. We did say, though, that any one blunder in transmitting the information from the DNA to the ribosome can result in a coding error that may make a defective protein. It may make a protein that doesn't work at all, or it may make a protein that's not sufficient. It's functioning close, but not the right way. This is a hemoglobin coding error, okay? There's 574 amino acids in the hemoglobin molecule, okay? And when synthesizing the hemoglobin to carry oxygen in our red blood cells, this sequence of 574 better be exact. If it's a little off, if a different amino acid is stuck in place where it shouldn't be, then the hemoglobin is going to be a little defective. It could be wildly defective, or it could be minimally impacted. So there's different expressions of coding errors that may not cause any symptoms at all, and it's just a finding. Or there are some that can cause real problems and diseases. When synthesizing hemoglobin to carry oxygen, if the amino acid valine is mistakenly substituted into the amino acid position where the correct amino acid would be glutamic acid, if we start putting this in place instead of that, we wind up with a hemoglobin molecule that's prone to change its molecular shape. You know, remember that big twisted up globular molecule? It can change its shape into a sickle shape. It can change from this shape into this. Maybe not all of it, but some of these cells may turn into it. And depending upon how much of this has been missubstituted, it may sickle more or it may sickle less. Okay. But once this stuff starts to change shape, it gets stuck when it's going through our capillaries, through our blood, tiniest blood vessels. And instead of flowing smoothly downstream, here, these are normal ones over here, these sickled ones bang into each other and they form a clump. Okay. This clumping obstructs flow downstream to the cells that this capillary is supposed to be feeding. And it deprives them of adequate oxygen, because that's what the hemoglobin carries. And if they don't have adequate oxygen going to these cells, they can't metabolize glucose into ATP, which is their energy source. And so if that's the case, people who are experiencing active sickling may not be there all the time, but if there's a situation that provokes this to happen, they will have body tissues that are not getting enough oxygen, which means they can't metabolize glucose, which means they can't function properly. And different organs are going to experience that to different degrees. They will have joint pain. They may be short of breath. If it happens a lot and clots off larger and larger vessels as this piles on, they may lose tissue. So just as that's an example of how this could play out. So it's the same 4 nucleotides in a different order that will give you a different amino acid. Okay. The different combinations of these nucleotides produce the amino acids that we can build. And by combining those amino acids in different orders and different lengths, we make all of the proteins in our body. So it's the ordering of the amino acids that has to be exact so that the protein is exact, so that it will be structurally exact and able to perform correctly. Okay. And remember, there's 9 amino acids that we cannot synthesize, that our DNA can't unfold and tell messenger RNA to go build this stuff. And so we need to get those amino acids dietarily. Okay. Now we keep talking about this adenosine triphosphate nucleotide, right? Here it is, the adenosine, the adenine, ribose, phosphate, right? The nitrogenous base, the sugar, the phosphate. Nucleotide, the ribose, phosphate, 2 phosphates, 3 phosphates, adenosine triphosphate. So this is the same adenosine that combines with thymine in DNA or uracil in your RNA, right? And when we link it with the sugar and the phosphate, it makes up the nucleotide, adenosine monophosphate, diphosphate, triphosphate. Okay. The electrons that hold this 3rd phosphate onto this big molecule are really high energy electrons. There's a lot of juice in those. And so if you were to lop this one off and free the electron, that's the source of your battery. That's our electrical activity. That's the energy we need to do all of these enzyme synthesis functions, conversion of bicarb to carbonic acid, to building proteins, to make things happen. This is it at the atomic level. So our energy release, adenine, ribose, triphosphate, ATP, right? dehydrogenate a piece of this, I have adenosine diphosphate, and there's my energy. Okay. So what happens is that the adenosine goes back into the nucleotide pool and it's recirculated to bind another phosphate with a high energy bond. And when that one comes off, it releases its energy and well, okay, we're back in the pot. Let's make another one. And round we go. Okay, it's recirculated to make more high energy ATP. Each cell has about 1 billion ATP molecules at any given moment. And it fuels that cell's needs for just a few minutes. Okay, which means it's got to be replaced. For every ATP, that third phosphate is added and removed 3 times each minute. We cannot store this molecule. As soon as it's made, we use it. It goes back into the basic structure pool. We find another phosphate, force it back on, and it's broken off again and releasing that electron over and over and over again. This is an interesting quote. Hooking and unhooking that last phosphate on ATP is what keeps the whole world operating. It's continuously recycled in our bodies. We will use up your body weight of ATP over the course of a day. Each molecule is recycled about 1,000, maybe 1,500 times during a single day. So as you make it, you use it. And then you have to make it again and use it. You know how those phosphates get forced onto that adenosine to make adenosine triphosphate? By enzymes. The enzymes are all made from amino acids that are coded for by our genetic code, transferred to messenger RNA using adenine, cytosine, thymine, and uracil to make each amino acid, except for the 9 we have to eat. Okay, if you have an environment that becomes too acidic or too alkaline, then the enzymes stop working. So it's a good thing we have a buffer system, right, to keep us in that 735 to 745 boundary. If you don't have enough oxygen around, like we showed with the sickle cell model, or if you don't have enough carbohydrates to break down into glucose, malnutrition, starvation, if you don't have insulin to get the glucose into the cells to begin with, then you're missing the fuel substrate that you need to even start the process to get 36 molecules of ATP out of every glucose. So you can see the crucial nature of these principles of the chemistry of life that make our bodies do what they're supposed to do. And as you go through the rest of the course, you're going to learn a whole lot more about organ systems and their normal functioning. And then really quickly, you're going to learn about what major things can go wrong with them, with those systems that are going to make people call 911 and look for you. It's really all about the chemistry. What have we done this morning? We defined matter. Okay, everything is made of matter. Matter is made of elements. Elements are made of atoms. Atoms have proteins, electrons, and neutrons. That's nice. Then we use symbols to name some of our common elements that are found in the body. Lithium, hydrogen, carbon, oxygen, all of that. We describe the purpose of ionic, covalent, and hydrogen bonds in our bodies, strongest to weakest, with the ionic bonds in the middle. And then we talked about what happens in synthesis and decomposition reactions so that we can make things or break things down into different products. We talked about how important water is to the functioning of our body. We talked about where we find water in the body, in the cells, in the plasma, extracellular, intracellular. We talked about the roles of oxygen and carbon dioxide in cellular respiration, in making ATP. We talked about pH. We talked about the normal pH ranges in body fluids, 735, 745. We talked about how a buffer system resists major swings in our pH. It gives us stability. It allows these reactions to take place. We talked about the functions and types of different sugars and fats and proteins, and we talked about how enzymes function as catalysts. We talked about steroids and how useful they are in making anti-inflammatory products and our hormones that we need. And we talked about potential badness if some of our lipids that we make start to accumulate on the linings of our vessels. We talked about enzymes as catalysts, taking parts, putting them together, making new things. And we talked about the function of DNA and RNA and ATP. I do not expect you to remember every single piece of this presentation. We just covered basic cellular biochemistry in 3 hours. There are entire courses and college majors in this stuff, and people study any one of these molecular steps for their entire careers, like we just talked about the 2 Nobel laureates. And we talked about Watson and Crick and their Nobel Prize. So several have been awarded for work revealing just how amino acids are made, how DNA works, and for the very structure of atoms, including Dr. Paul Boyer, who is a biochemist at UCLA, who won the Nobel Prize in Chemistry for 1997, talking about the enzymes that underlie the synthesis of ATP. Pretty critical stuff. You have survived, I hope, since I can't see you all, you have survived the chemistry of life. The whole point of this was to give you an understanding of the chemistry of the human body and how things are supposed to work, how unbelievably similar we are, and how good that is for our being able to understand why things are supposed to work the way they work, and what can happen when they don't. And why patients present the way they do when things start to go wrong. And they're going to call you for action to stabilize them while they're in your care. So it's a big deal. It's safe for you to return to your level of consciousness wherever you last left it. So again, I mean, it is my honor to be able to talk with you about this, knowing what you're in for as a career, knowing how crucial it is for people who are going to be calling upon you in moments that, over the terms of your career, may turn out to be seemingly trivial, but to them, it may be really important. So it's all part of differentiating our differences from how 99.9% similar we are. Work hard, do well. You're going to serve critical functions. All right. Be well.